Okay, so hello everyone. So now we are starting with another topic of like how to design a comparator, a 2-bit comparator using Karnaugh map. Okay, so now if you look at the comparator, so assume that now this is a comparator. We are comparing two quantities AB and CD. What is the size of AB? How many bit data? 2-bit data. What is the size of CD? 2-bit. Okay, now there are different values. When AB is 0 1, AB is 0 1 and CD is 0 1. Okay, what about equal? Are they equal? 0 or 1? 0. AB is greater than CD? 0 or 1? 0. AB is smaller than CD? Yes. 1. Again, now we are comparing AB. Assume that the value of AB is 1 1, CD is 1 1. Are they equal? Yes. What should be there? 1. Are they smaller? Greater? 0. Smaller? 0. Again, 1 0 and CD. Which value is this? 2 and then 0. So AB is smaller than is equal to. Are they equal? 0. Then 1 and then 0. Got it? So now we go for all of the possible. Okay. So how many possible combination for the variable AB and CD? How many possible combination? AB and CD. How many? If we combine them, 4 bit. How many possible combination? 16 combinations. So now if you look at this comparator, so this comparator is computing the equal. So now this is, what is this? EQ equal LS and then GT. Okay, so now this is actually these are okay. Now if you look at the function, so now we have how many functions? How many functions at output? How many functions? 3. So the input is how many bits? 4 bits. The output is 3 bit. So now we have 3 functions. So 3 function. The first function F1, F2 and F3. F1 is a function of A, B, C, D. F2 is a function of A, B, C, D. So now this is a problem. I may give you a problem. Okay, now design a truth table for the comparator. So now design a. So now this is the. These are all of the possible combinations. All of the possible combinations. And if you look at the F1, what is F1? What is F1? Yes, please. Equal. So when they should be equal? For 0 0 0 0 0 0 0 0 0 0 and 0 0 they are equal. 0 1 0 1 they are both equal. 1 0 1 0 they are equal. 1 1 1 1. So can you see here this F1, the first one, the blue one? Please look at the blue one. In this case, A, B and C, D are equal or different? Equal.
Why is 1001 is not equal?
Which one?
1001.
1 0 and 0 1. So we are comparing bit by bit.
Okay, but 10 is 0 and 01 is also 0, so they are equal.
No. 1 0. So we are comparing 2 bits. Okay. So this is the MSB and this is the LSB. So 1 0 is mean 2.
So you don't. It's not an AND gate.
No, it's not an AND gate. So if you look at here, so now AB is a 2-bit data. It's a 2-bit data, and CD is a 2-bit data. So can you see here? Okay, now. So please, what is AB? AB is what? 1 0. And CD is what? 0 1. If you transform this into binary decimal, it becomes what? 2 1. So 2 is greater than 1. So GT will be 1. So 1 0 0 1. So greater is 1. No, that's not an AND gate. You got it or not got it? So now at this point of time, do you see? Do you hear my voice? Do you hear my voice? I start recording because you want to. Hello. Yes, I think it's working. Got it or not got it? Similarly, we also have the other. Okay, now look at this. Now F2. What is F2? Now if you look at here, how many possible combinations are there? How many possible? 16. For how many combination equal is 1? 4. How many combinations are left? 10. 10? No, 12. 12 outcome. So out of this 12 combination, for 6, less than is 1. and for 6 combination greater than 1. So can we see here? So this AB is equal to C. How many combination? 4. How many combination? 6. And how many combination? 6. So it means that now they are mutually exclusive events. That are mutually exclusive events. If two quantities are equal, so their greater than and less than will be 0. If it is greater than is 1, so the less than and equal will be what? 0. So if you look at each row, 0, 1, 0. F2, what is F2? Smaller. 0, 0, 1. What is F3? Greater. So it means AB is greater than. So now these are all the combination. Can you see? AB 0, 1, 0, 1, 1 is smaller than 2. Any question? Should we proceed? Okay. Now we have three functions. Okay. If you look at the function F1, what is F1? AB is equal to B. CD. What is F2? AB smaller than CD. What is F3? AB is greater than CD. Okay. Now all of these three function is a function of how many variables? 4 variables. So we need how many Karnaugh map? A Karnaugh map is 16 entries. Now we want to solve it for F1. This is F1. How many ones are there? How many ones? 4. And please don't ask me. I will not solve this again and again. Karnaugh map. Okay, now can you see 0, 0, 0, 0? They are same, equal. 0, 1, 0, 1, same. 1, 1, 1, 1, same. 1, 0 and 1, 0, same. F1 is what? Equal. A and B and C and D are. Got it or not? We have now 4 ones. And then we solve this using Karnaugh map. And you know, I'm not going to explain this. If you look at this entry, how does it this? This is actually A, B bar, C, D bar. I will not going to explain Karnaugh map again and again. Because you know, I will assume that you know the Karnaugh map. And how to transform a truth table. So now we have transformed this truth table into Karnaugh map. Got it? Now we want to have F2. Forget about thing. How many ones should be there in the Karnaugh map? 6. So now just put all these 6. So these, and these are 6 ones. We can make a big square of 4. A bar C. Again, I'm not. Can you see? A bar C. The same thing. And in this is all color coding. A bar, B bar, and C. Got it? Now we got expression for it. And now F3 is for exercise for you. You can also have. In F3, how many ones will be there? 6, and you can also derive it. So this is also homework for you. Okay. Now, if you look at this problem, and in this problem, we have a logical description. We have transformed that logical description into a truth table. And from that truth table, we have derived 3 functions. And what are these functions? F1, F2, and F3. And from that truth table, we draw the Karnaugh map, and then we got the expression for F1, we got the expression for F2, and we got the expression for F3. So in the exam, I may give you a logical description, and then you design the complete system on your own. Got it? Okay. Now we also want to do. Now we have given a description that okay. Now we want to compare two bit is a 2-bit comparator. It is a 2-bit comparator. We are comparing 2 bit quantities, which maybe we call this as A1 and A0 and then B1 and B0. We are comparing A and B. Okay. Now we have another description, another problem. Now we want to have a don't care really means I don't care. Remember the BCD implementation. What are the don't cares conditions? For BCD, what are don't care condition? 10, 11, 12, 13, 14, 15. Remember? So that's the reason that I asked one question in the BCD, because I'm going to. Okay, now we have a function. And this is called BCD increment function. What is BCD increment function? If the input is 0, what will be the output? 1. We say we are incrementing. On the left hand side, ABCD. If the code is 0, what will be the output? 1. If it's 1, 2. It will become, if it's 8, 9. If it's 9, 10 is valid? No, it will become 0. So it means 0, 0, 0, 0. You got it? So now, okay, now the input is BCD, the output is BCD. What is the input? Can you see here? Now we draw it again. Where is the tester? Okay. Now So now we have BCD increment function. So this is increment. What is the input? A, B, C, D, and A is the MSB. So this is what BCD code, and what is the output? W, X, Y, and Z. This is also what? BCD. It will range from what? 0 to 9. It will also range from what? 0 to 9. But when we add, if the input is 9, the output is 0. Remember your stopwatch. When it becomes 5, 9, it becomes what? 0, 0. So that's the reason. It's overflows. So for this case, so now the above case are valid or invalid? Valid. Yes, please.
A1001, why don't we make it also I don't care?
No, but the output is weak. Okay, we can also define another signal, overflow. So we can have another signal, overflow. For all these cases, for the 8 combination, overflow will be what? 0. And for this case, 1. So we can also do that. Up to you. Up to you. But when we say when the output is 0, automatically it is an overflow. When the output is 0, it is an overflow. Because you add 9 to 1, there is an overflow. Got it? So now, and we can derive it from here. What is overflow? In this case, overflow is 1. Yes. What is overflow? W bar, X bar, Y bar, Z bar. We can directly do it without doing any minimization. Got it? So now, if you look at here, you know how to derive this function. If I give you so in exam, I may give you the problem. Design a BCD incrementer. The input is A, B, C, D, and the output is W, X, Y, and Z. If I say design an BCD incrementer, the input is K, L, M, N, and the output is P, T, C, B. That's the input and that's the output. This is just like the name of the variables. In this case, what is A? MSB or LSB? MSB. What is W? MSB. So you need to know what is the MSB and what is the LSB. Okay, now if you look at here, okay, now if you look at W, how many ones are there in W? 2. How many ones are there for X? 4. How many for Y? 4. And how many for Z? 5. So it's all. So this is just like, so what's your job? So now we have 4 functions. What are the name of these functions? Please help me. W is a function of what? ABCD. Y is a function of ABCD. Z is a function of ABCD. W, X, all of these variables are a function of ABCD. Got it? Any question? Any question? Should we proceed? Okay, now. So now we have this, and then we draw this. And why we have don't care? Why we have 6 don't care? Yes, please. You ask the same question. Why we have 6 don't cares? Yes. I'm asking you. Why do we have 6 don't cares? Why do we have 6 don't cares?
Because we still
Remember, what are the invalid codes? 10, 11, 12, 13, 14, and 15. 6 codes are invalid. You ask the same question. Yes, remember? Why we have 6 invalid codes? Why? No, 6 invalid combination. So if it's over the 9, 10, 11, 12, 13, 14, 15. How many combination? 6. So there's the reason. How many don't cares are here? 6. Got it? Any question? And it's also here. Why 6? Don't care. And you can also draw this heavy it from the these are valid combination or invalid combination? Invalid. How many ones for W? 2. How many ones for Y? 4. You can count them. And then you dot it. So Z we don't care. Okay, now I'm not interested in W, X, and Y. It's your homework. It is your homework. We want to derive an expression for what? Z. We want to derive an expression for Z. Okay, now look at here. And W, X, and Y is your what? Homework. It's your homework. Yes, please.
the previous slide. Shouldn't the 10 also be invalid? Yeah.
Which one?
10, like the 0, 0, 0, 0.
Increment of 9.
Increment of 9. Yeah. Shouldn't that also be?
No. It is an overflow. It is an overflow. Let's assume you have a stopwatch. This is 9. 9 will become what? 0. This is an overflow. So now 9 it is an increment. So in this case overflow will be 1. And in this case what will be overflow? 1. W bar, X bar, Y bar, and Z bar. Got it? Okay, now if you look at here, we want to find Z without don't care. For without don't care, we are not including the X. There are 4 ones, and then these 2 ones, B bar, C bar. Okay, and we don't care. If we include don't cares, the whole, what is the expression? D bar. Which approach is better? Including don't care or excluding don't care? Including don't care. The logic expression is further minimized, because if we combine this don't care with all these things, so we have a big group and all of the ones are covered, all of them. So now this is, so similarly, this is your homework. You also find an expression for what? W, X, Y, and Z with don't care and without. I may ask the same question in your midterm or in quest. Is a hint. I'm not going to explain it. Yes, please.
Using the don't cares in the essential prime ingredients, doesn't it mean that the don't care values are 1?
No, it doesn't. You should not include all of the X in the prime implicants.
No, like whatever we include in our essential prime ingredients,
Yeah.
where X is, we are taking them in our boxes.
Yes, we can take this in boxes.
It will mean that the X is 1 since we are constraining.
No, you don't, because if you look at here, these 3 are not covered. So
The
you,
other ones stand for 1, right?
yes, it's for 1. It stands for 1. So this is a part of the prime implicant. Yes, it's a part of the prime implements. But if you do not cover an X, it's not an obligation. But if you look at this, these 3 are covered or not covered? Not covered. So you don't need to cover them. These X are as a helping hand. This is not. You don't need to include this. Got it? This is all. Any question? Should we proceed? Yes, please.
How do we include all the functions together?
Which one?
How do we include all the functions? Like how do we include Y?
They are not together. They are different outputs. They are different outputs. So we have one circuit. So now maybe I'm not going to explain. So now we have one circuit. Now we have another circuit. We have a third circuit. We have 4 circuits. So it may be some AND gate, some combination. This is output 1. We have some gates. We have output 2. We have some gates. We have output 3.
Then how do you combine all the outputs?
So now if we combine all these outputs, so if you look at here, so how many outputs are there? 4 out. So this is wire 1, wire 2, wire 3, and wire 4. I will explain this in the next slide. I will explain in the next, and I will answer your question because we have some problem here. Okay, now, and I will explain this. Now I will explain your question that how do we. Now if you look at here, suppose we have 2 functions. F. Okay. What about F and G? How many functions? 2 functions. How many variables? 3 variables. Got it? So F is a function of ABC, G is a function of ABC. So can we say, now this is 2 separate circuits, and these are what? 1 circuit with 2 output. Got it? Okay. Now if we have 2 functions, ABC, F and G, how can we minimize it? We minimize each function using K-map separately. What is this? K-map of F. How many ones? 4 ones. Now we got this expression. Now we have another function. What is this function? G. And we implement it to K-map. I'm not going to explain K-map because I assumed that K-map, K-map. Is there any observation? Yes. What is observation? AB is common. AB is common. So if you treat this separately, okay. So if you treat this separately, so now we have, okay. Now this is your answer. We have multiple outputs. This is F and G, and multiple inputs. What are the multiple inputs? A, B, and C. So if you look at here, this is SOP expression or POS expression? SOP. This is the sum of the product expression. How many AND gates? 4. How many OR gates? 2. Now this is the function. So in that case, in the BCD case, we have 4 output, W, X, Y, and Z. For W, there will be some gates on the left hand side. For X, there will be some gates on the X. Similarly for Y and Z. Similarly for F and G here. Okay. Now what is our observation? Which gate is common? A and B. So do this. We have common term. So we do this. So now, if you look at here, which implementation is better? The first one or the second one? The second one. Why? In the first one, so we further reduce it. Okay, now if you treat each function separately, okay, we are doing some minimization. But if we combine these 2 circuits, this is called as logic sharing. So now this gate is providing the input to this gate, and this gate is providing the input to this gate. Yes. But inverter is, yes, so now you have this A and then inverter from A bar and yes, of course, why not? So this inverter for A is shared 2 times, and very good, very good. Now you know he understood everything. Very good. So now we have multiple. Now this is example number 1. Now we have example number 2. Now if you look at how many functions do we have? 2. How many variables? 4. What should be the size of the Karnaugh map? 16 for both function. So now what should we do now? What should we do? Yes, everyone. Draw KMF for what? F and G separately. Now if you look at F, how many ones? 1, 2, 3, 4, 5, 6, 7. For G, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Again, simple. Okay, don't ask me how did we get it, because you know, I assumed it, now you know Karnaugh map. How many ones? 7. How many ones? 6. Solve it. And you know you are more expert than me. I also use the color coding. I solve it. So can you see here what is the expression? Now there is an observation. Yes, please help me. Help me. Look at here. Look at all the expression. Look at the expression and what is your observation? Everyone. Yes, please. Is there any observation for you? Do we have some common term? Do we have some common term? Look at here. Everyone. Which one is common? Yes, A bar D and AC are common. A bar D. Can you see here? In this expression, we have A bar D. And in this expression, A bar D. And then AC. This is common. Okay, now extract a common term for F and G. So can we write it like this? Please look at here. What is T1? This is A dot. This is top. What is T2? AC. These are common. Can we rewrite the expression? What is F? T1B. T1 is what? A bar D, B. Okay, T2, AC. This is T2, AC. And then what is this? AC, D bar. Got it or got it? Now we extract a common term. And what is the advantage of this? If you look at the, okay, now if you look at the expression on the left hand side and expression on the right hand side. Okay, now please forget about inverter. Forget about inverter. How many gates here? Total number of gates, not AND and OR. How many gates? 7. 1, 2, 3, 4, 5, 6, 7. And how many gates here? 1, 2, 3, 4, 5, 6, 7. Huh? No advantage.
No, sir, because before it was a 3 input.
Yes, he's more intelligent. He's more intelligent, you know. Can you see here? This AND gate is a 2 input AND gate, and this AND gate is a 3 input AND gate. So if you want to buy, okay, now this is the gate level implementation. This is the gate level implementation. Who is electrical engineering? Raise your hand. Oh, for electrical engineering. So maybe in the terms of electrical engineering, you will transform these gates into transistors. When you have some transistors, so you have here we have more transistor. Here we have less transistor. So if you say maybe for 3 input AND gates we have 6 transistors, now for this we have 4 transistors for 2 input AND gate, and for each transistor it has some input capacitance and output capacitance. And the critical part, if there are 3 transistors in series, more delay. If there are 2 transistors in series, less delay. So that's the reason that these circuits will be transformed into some kind of transistor internally. I'm not going to tell you the details. You know, the electrical guys will answer me this thing. Okay, so now if you say, now we are also doing the logic sharing, and for this logic sharing, so now this AD, so this output of AD is going to the input of this AND gate, and this to the input of this OR gate, and similarly the output of this AND gate will go to this OR gate and this AND gate. And now we have reduced the number of transistors. And now look at a chip. A chip consists of billions and billions of transistors, and these logic minimization help us to reduce the number of transistors and to reduce us the cost. Not only the fabrication cost, but also the delay cost. Got it? Because can you see here, maybe a 3 input delay gate, maybe it has a delay of 1 nanosecond, and 2 input gate may have a delay of 0.8 nanosecond. 1 nanosecond is better or 0.8? 0.8. This is how it works. Any question? Should we proceed? Okay, now, so we have the CAM map. So we have, if we have different functions, we can solve this independently. But if we have multiple functions, of the same inputs, we can combine them, extract a common term. So what is the objective? We can either do the, okay, now there are a lot of methods. We have different implementations. We can have the SOP implementation. We have the POS implementation. We have the NAND implementation. We have the NOR implementation. Now using Karnaugh map, we can extract into the SOP implementation and the sum of the product implementation. And if you have two different functions, this Karnaugh map is not efficient that much. But if you have multiple circuits, we can also use the logic sharing approach. This approach is called as what? Logic sharing the gates. Any question? Should we proceed? So, okay, if you want to solve, if you have any function, we will draw the truth table. From that truth table, we will do the minimization, and then we identify the shared terms, and then we use the shared term to further reduce the cost. This is called as a multi-object optimization problem. Okay, now, so if you say, now we are here, now we finish with this thing, now we are having with another topic, and this topic is a combinational circuit. And this you know, it's a very important topic. It's a very important topic. So now we have two classes of combinational circuit and sequential circuit. Sequential circuit we will study later on. So now, can you see here? Now we have combinational circuit. Any combinational circuits. How many gates? How many gates? 6 gates. 3 inverters, 2 OR gate, 1 AND gate. Okay, how do we analyze this circuit? Okay, we define some, label the inputs and outputs. Yes? What are the inputs? A, B. What are the outputs? A, F2. Obtain the function and the intermediate points. These are the intermediate points. So the intermediate points are A plus B, A blah plus B bar. These are the function. Draw the truth table. We draw the truth table. Got it? And deduce the functionality. Now, if you look at this function, look at it. What is the function? What does this circuit doing? What is F1 and what is F2? Look at the circuit. What is F1 and what is F2? Yes, please. Help me. Help me. What is F1? Deduce the functionality. Now, in the previous case, we have the functionality. What was the functionality? Comparator. What was the functionality? Comparator. And then we deduce some expression for W, X, Y, and Z. Got it or not got it? Then we have another function. What was the name of the function? BCD increment. That was the function. We want to solve that objective. Then we draw the truth table, we do the Karnaugh minimization, and we do blah, blah, blah. Now, if you look at here, now we have the circuit. Now identify what is the function. What's this circuit doing? Look at the function, F1 and F2. Exclusive OR. It isn't the sum of 2 bits. 0, 0. We want to perform 2-bit addition. 0, 0, 0. 0, 1. 1, 1, 0, 1, 1, 1, 0. It's a 2-bit addition. Okay, now this F2, it's a carry out. 1, 1. If we add 1 and 1, sum is 0, carry out is what? 1. Got it or not got it? So now this is the deduced functionality. So this is a 2-bit adder. This is a 2-bit adder. Okay, now what are the example of 2-bit adder? Okay, now please look at here. So please help me, everyone help me. So now we say 0, 0, 0, 1, 1, 0, 1, 1. This is your sum, C out and sum. 0, 0, we add to 0, 0. Sum is what? 0. And carry out? 0. This is a single bit addition, the same thing. 0, 1, sum is 1, carries what? 0. 1, 0, carries 0. 1, 1, sum is 0, carries 1. So can you, if you look at here, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 2, this is 2. So this is 0, 1, 1, and 2. Carry out is the MSB and sum is the LSB. Got it? So now this is what? A 1-bit adder. This is a 1-bit adder. Okay. Now the F1 is the sum and F2 is what? See out. Now we have a half adder. So if you look at here, now we have a half adder. Half adder. The input is what? X and Y, and the output is what? SSC. So now we call this X is Y. I'm calling it here what? Maybe A and B. Up to you. We are adding to 1-bit adder. So this I call it here sum. I call it here what? S. S stands for what? sum, C out, carry out. Do we have carry in? No. If you don't have any carry in, this is called as the half adder. And if we have a carry in here, this is a full adder. Half means no carry in, and half full with a carry in, and half without carry in. Got it? Any question? Any question regarding this? So now we have an half adder. Draw a truth table. Now this is a truth table. So can you see here 0 0 carry 0, and then here this is 1 bit addition. Any question? Any question? Yes, please. We are okay. Again, we are adding. Now let's assume we are adding this 0 0 1 1 1 0 1 1 1. Okay, so maybe this is 1. 1 1 is what? 0. It become carry in. Are you taking this carry in consideration? No. So the full adder also takes the carry in consideration. And I will explain this after some slide. Can you see? Okay, now gate level, half adder. This is the gate level. Okay. Now if we have this function, S stand for what? Sum. C stand for what? Carry. Now we have a single one. So C, what is C? X, Y. And then what is S? X bar, Y, X plus Y. Got it? Any question? Simple. Write a logic diagram. So this is 2-bit adder. No, 1-bit adder. X is 1 bit, Y is 1 bit. Half adder, not a full adder. Okay, now please look at here. At everyone, I need your attention. Everyone, I need, and this is the way. Maybe I will ask. I will definitely ask some question from the adder. Okay, now if you look at here, we have the sum is output, X and Y are the inputs, and thing like. Now this is called as the AND OR logic. The AND OR logic for what? SOP expression. For what? SOP expression. How do? We do the Karnaugh map, we do all the magic, and we derive this expression. This is called as what? AND OR logic. Now we can also have the OR AND logic. Which expression? POS expression. So this is another implementation. Same 1-bit adder. One implementation is different implementation. Different. Okay, now again, assume I want to do some kind of repetition structure in CMP 120. Repetition structure. I want to add the sum of all elements of array. Which loop will you use? But you can also use while loop. You can also use do while loop. Yeah, so that's the thing. So we have the same problem but different implementation. So similarly, we have the same logical expression but we have different implementation. This is implementation number what? 1. This is implementation number what? 2. This is the logic sharing approach. We do some magic. I'm not going into the magic, but this is called logic. Which now we are sharing this what? XY. We are doing logic sharing. The same adder, but with logic sharing. We also studied logic sharing. Any question? Should we proceed? Okay, now can you see here? Now, what is this called? Mixed gate approach. Because we use one exclusive OR gate and one AND gate. How many implementations? 4 different implementations. So if in the exam I may ask, I may give you one functions. I can say, okay, implement using SOP, implement using POS, and you know how to convert into SOP expression. You know that. You will draw the Karnaugh map, you will draw the command and derive the SOP. The same thing for POS. You will draw the Karnaugh map of F bar, apply the De Morgan theorem, all these things, because I'm not doing to do it again and again. You need to do it on your own. So go home and do all this problem on your own. Okay, assume that this is a problem of any. I'm not going to say, oh, I should not do it. Okay, now we have this half adder or full adder. No, now we have full. Previously we studied half adder. Okay, now binary addition. Now if you see here, now we can say, okay, I will explain this with an example. So assume that we are adding some quantities A0, A1, A2, B0, B1, B2. What is the size of A? 3-bit. What is the size of B? 3-bit. Assume that C in is 0. C in is 0. So now C in. So we add C in A0 and B0, then it will give us S0 and it will give us some C out. This C out will become what? C in for the next stage. This will become the C in, then we add C in A1, B1, then we got what? S1, yes, S1. So we can say this is C1 and now this is what? C2. C2 is the output from this stage and the input to the next stage. So this is C0, this is C1, this is C2 and blah blah blah. Got it? So we need a full adder. So in the full adder not only consider A and B but it also consider the C in from the previous stage. So can you see here? So for here C in is 0. This is S0 and C out. C out will become carry in for the next stage. Then we carry in for A1 and B1 and then we add C1, it will become S1, it will give C2, C2 will become carry in for the next. Got it? So we need a full adder and full adder also consider the carry in consideration. So if you look at here, now we have, please remember, we have 3 bits, 1, 1, 1. What is the maximum value that we can have? 1, 1, 1. 1, 1, 1 is what? 3. 1 bit, 1 bit and 1 bit. What is the maximum value of A? Either it's 0 or 1. What is the maximum value of A? 1. What is the maximum value of BI? 1. What is the maximum value of CI? 1. 1 plus 1 plus 1? 3. 3 to represent 3. How many bits do we need? 2. Got it? 0, 0, 0. The result is 0. This is the MSB and this is L. 0, 0, 1. 1. 0, 1. 0, 1, 0. 1. 0, 1. 1, 1. 1 plus 1. 2. 1, 0. 1, 0, 0. 1. 0, 1. 1, 0, 1. 2. 1, 0. 1, 1, 0. 2. 1, 0. 1, 1, 1. 3. 1, 1. Got it? This is the same thing. So we say this is 1, 0 and C in is 1. 1, 1 in the same thing you did in the binary addition. Sum is 0 and carries out is 1. Same thing. But now we want to do this. So this is, okay, if you look at here, now this full adder, we have 2 outputs. What is the name of the first output? Carry I plus 1. What is the name of the second output? SI. What are the inputs? AI, BI, carry I. So actually carry I plus 1 is a function of AI, BI and carry I. And SI is a function of AI, BI and C. Again, what should we do now? Karnaugh map and blah blah blah. Okay, now. So this is a full adder. This is the truth table. Got it? We can use it using Karnaugh map. Yes? Okay. What should be the size of Karnaugh map? 8. 8. How many Karnaugh map we need? How many Karnaugh? Yes, please. How many Karnaugh map you need? Yes. How many Karnaugh map you need? How many Karnaugh map you need? 2. Why 2? Can you see here? In the blue, we have 2 functions. What is the name of the first function? C. What is the name of the second function? S. So we have 2 functions. So we need how many Karnaugh map? 2. One for C and one for S. And now all of these 2 functions is a function of what? 3 variables. What are the name of 3 variables? Very good, very good. That's very good. That's the real spirit. Okay, now if you look at here, now we need 2 Karnaugh maps. Okay, for C, please look at here. For C, how many ones? 1, 2, 3, 4. For sum, 4. Got it? We do all the magic. Yes, I'm not going to explain it because this is, Karnaugh map. Can you see here? I'm also using the color coding. I can't do more than that. I'm again explaining. So now, how do we derive X, Y for this blue? What is changing? X is same and Y. Same thing. Please go through and please do all these problems at home on your own without going into detail. How do we go for S? Okay, now, can it be further minimized? No, we cannot have group it. So can you see the color coding? What is this one? Please help me, give me the expression. For 1. Yes. 0, 0, 1. X bar Z. Color coding red. For the blue one, got it? So we have the color coding. Any question? Should we proceed? Okay, now please look at here. Now we did some expression. Now this is the expression for C. And now I'm doing algebraic manipulation. There is a reason for that. Please don't ask me that how did we do. You know algebraic manipulation. Now I'm doing some algebraic manipulation. This is some magic. Can I write it? What is the common term? Z. Okay, can you see the red one? I expanded. So this is x, xy plus xy bar. So this is x and this is y. Can I, okay, now which term is common term? Xy is common, xy is common. So I take it only once and then xy bar plus x bar y. Got it? Okay.
Where did Z go in the third equation?
Oh, Z is here. I'm sorry. Z is here. Okay.
And how did we get X bar plus X y bar?
Which one?
They
We expanded. Show the color coding. So x is equal to xy plus xy bar. I'm expanding it. Expanding. Got it? And now Z is here now. Got it? Is this here? Now it's here. So can we see the green thingy? Exclusive OR. I again expanding it. So this is my expression for C. This is my expression for, and again I'm doing a lot of magic. This thing. Got it? Now there is a reason for this. Please, there is a reason for it. And I need your attention. Don't look into your mobile. Otherwise, you will be penalized. You have to. Okay. Now, if you look at here, C is equal to xy. We got this magic expression from here. Can you see which one is the common term? Exclusive. Yes, I. This one is the common term, and this one is all the term. Now there is a reason for that, and I will explain it. Anyone has some observation? Please look at the observation. Now, are we designing a full adder or a half adder? Full adder. I want your observation. Yes, but if you look at this block, what is this block? It's in half adder. It's a half adder. So full adder is made of how many half adders? 2 half adders and what? 1 OR gate. Got it? And before that we derived the expression for the half adder here. What is this? Half adder. Now what we are doing here? We are doing full adder, but we are using the half adder using full adder. Got it? So how can we implement full adder? So now please look at here. Now again in the next slide, and this is I'm going to this in a very incremental and gradual way. Okay, now please, this is also another implementation of the full adder. Why it is another implementation of the full adder? If you look at here, so which approach we are using here now? On the left hand side, sum of product expression. Minimize or unminimize? Unminimize. Got it? So can you see here? So now it is, which expression is this? And or logic. Okay, now if you look at S, which color? Red. How many ones? 4 ones. 1, 2, 3, and 4. So how many min terms? 4 min terms. Got it? Okay, for carry, how many ones? 1, 2, 3, 4. How many min terms? 3. Why? Because this is reduced. Because you have big groups, and S for S we don't have any reduce. Got it? Which implementation? This is AND or logic, which is called as the reduce of expression. Got it? Okay, now if you look at here, and we also did some magic. So we derive an expression for C using which method? Karnaugh map. We also derived expression for S. And now this one is implementation number 1. This one is implementation number 2. Now in implementation number 2, what we are doing? We are doing logic hearing and algebraic manipulation. It was slide number 12. Please refer to slide number 12. We did it. Okay. And now if you look at here, what is these two things? Half adder. What is this thing? Half adder. So a full adder can also be implemented using two full adder and two half adder and one OR gate. So now this is another implementation. So think. So there are a lot of ways to implement a function. There are a lot of ways to implement a function, and then you can do it. Okay. Now please look at here. Now this is another implementation. Now we have the gate level implementation of a full adder. Got it? SOP of a 1-bit adder. Now please look at here. How many ones in carry? 1, 2, 3, 4. How many ones in SI? 4. 1, 2, 3, 4. Okay. Okay. Now if you look at here, for this expression 1 and 1, what is this? A, B, C. A, B, C. I'm calling it carry I. A, B, C. This is A, B, C. And this A, B, C goes here and is here. It's called as logic sharing. Got it? Now look at other expression. This expression 1, 1, 0. A, B, C bar. A, B, C bar goes to carry. A, B, C bar. Where is A, B, C bar? A, B, C bar. Where it goes? Carry or S? Carry. So this is the implement. So you can derive this. How many AND gates? 1, 2, 3, 4, 5, 6, 7. Not 8. Why? Because for this combination 0, 0, 0, this is not there. And this one is shared. This one is shared. Any question? Should I proceed? Okay. Now, so this is another gate level implementation of a 1-bit adder. Reduce or unreduced? Reduce or unreduced? Unreduced. The previous one was reduced. This one is unreduced. So we have different implementation. How can we implement a full adder? 2 half adder, 1 OR gate. Got it? We can implement a full adder using AND OR logic. We can implement a full adder using OR AND logic. We can implement a full adder using logic sharing approach. So these are different implementation of the same adder. So in exam, I may also give you the question of like, how can we implement a full adder, and then this is it. So now there is a question: how to design a combinational circuit? How to design a combinational circuit? We have some specification. Yes, elaborate. Anyone elaborate it? What is specification? Everyone elaborate. No, the specification. Specification is from the user.
What the circuit?
Yeah, what's the circuit? So I will give you an example. We did a lot of example. Give me that example. What is specification? Design a BCD incrementer. Specification. Design a 2-bit comparator. Specification. Convert BCD to XX3. Specification. Did you do this? Yes. Did we convert BCD to XX3? No. This is a specification. When we have the specification, from specification, what should we do? The next step, draw the truth table. Okay. Now draw the truth table. When we draw the truth table, what should we do? K-map, logic minimization. We have different functions, F1, F2, F3, and F2. What should we do? Solve them. Get the simpler equation. But when we get the simpler equation and we have different function of the same input, then we can do what? Logic sharing. Then the logic sharing and the logic minimization. So how can we implement logic minimization? We can implement the logic minimization using different technique. Algebraic manipulation. We can use K-map. Even the algebraic manipulation and the K-map will give us some reduced expression, but it is simplifying each individual expression individually, but not collectively. So collectively do what? Logic sharing. When we do the logic sharing, then we map a technology mapping. The technology mapping. Oh, the technology. Should we implement to AND OR logic? Should we implement to OR AND logic? Should we implement into a NAND implementation, or should we implement to a NOR implementation? This is called as technology mapping. And finally, we verify the circuit. How can we verify the circuit? We give some inputs and check the outputs. whether the output is correct or not. And I think you should have done this in your digital logic design system lab. Okay, now go for that. And we will do all these steps one by one. Another example. Now, code converters. What are the code converters? So the code converters take an input code, translate to equivalent output code. What is the example? BCD to XX3. What is XX3 code? XX3. So when we add 3 to the BCD, it is called as XX3 code. So if the input is 0, what will be the output? 3. If the input is 1, 4. If the input is 4, 7. If the input is 5, 8. If the input is 9, no, not overflow. XX3 is 12. So what is the range of XX3? From 3 to 12. What is the range of BCD? 0 to 9. Got it? So the range of what is the valid code for BCD? 0 to 9. What is the invalid code? 10 to 15. What is the valid range of XX3? 3 to 12. What is the invalid code? 0, 1, 2, 13, 14, 15. Got it? Now, how? Please, everyone, put pen and pencil. What is the input? BCD. The output is XX3. Draw the truth table. What is the input? BCD. So ABCD is the input. ABCD is the input, and W, X, Y, and Z is the output. Which code is this? XX3. Which code is this? BCD. Draw the truth table. How many don't cares do we have? 6. Please do it. Quick. I'm coming to everyone. Yes, please. Okay. I will ask some question from each individually. I will not draw the complete truth table, but I will ask some question individually from some students. Yes, please, Adli. Yes. A, B, C, D. W, X, Y, and Z. If the input is 0, 0, 1, 1, what is the output? 6. What is this? 0, 0, 1, 1. 3. What is the output? 6. Yes. In the back. You in the corner. Please help me. If the input is 0, 1, 0, 0, what will be the output? 7. How can I write it? Got it? Okay. Nas, please in the back. Help me. Please, you help me. If the input is 1, 0, 0, 0, the input is 8. What is the output? Help me. Input is what? 8. Okay. 1, 2, 4, 8. Because this is 8. 8 plus 4 plus. Got it? What will be the output? If I add 3 to it, what will it become? 8 plus 3. Yes, please help me. If the input is 8, what is the output? 11. How can I write 11? What's 8, 4, 2, 1? 1. Very good. 1, 0, 1, 1. This is what? 8 plus 2 plus 1. Got it? This is 11. Help me. The guy in the, please. If the input is 0, 0, 0, 0, and please help me. What is the input? Please, yeah, that guy. Yes, you. If the input is 0, what will be the output? If the input is 0, what will be the output? No. If the input is 0, 0, 0, 0, it is 0. We add 3. What did it become? 1, 1. No, 1, 1. Because the input is 0. The thing is, So can you see? If the input is 0, the output is what? 3. If the input is 1, what is the output? Help me. 4. If the input is 2, what is the output? 5. So if the input is 0, 0 means 0, 0, 0, 0. The output is what? 3. This will become 0, 0, 1 and 1. Got it now? Okay. So now, if you look at here, everyone, please compare it. So now this is the truth table. The input is 0, the output is 3. The input is 1, output is what? 4. Okay. Now if you look at here, so this XX3 code start from what? 3 to what? 12. And all of these the last conditions? Don't care. These are all the don't care. So how many functions do we have? 4. So it means W should be a function of ABCD. X is a function of ABCD. Y is a function of ABCD. Z is a function of. How many Carnot map do you need? 4. How many ones? Depend on the function. How many don't cares? 6. In all cases we have 6 don't cares. Got it? Now we do the logic minimization. K-maps. How many K-maps do we need? 4. K-map 1, K-map 2. This is the K-map for what? W. How many ones? 5. Color coding. See the color coding. Red one. How many ones? 5. How many ones? 5. How many ones? Got it? And then we do the logic minimization, do some tricks. I'm not going to do the logic minimization because I'm not going to explain it. I have explained it so many times. So we do all these things. So this is the expression for W. This is the expression for what? X. This is the expression for Y. And this is the expression for Z. Got it? Now, if you look at here, now we have used X as don't care. Can you see the color coding? Can you see here? Red, red. Then blue and blue. And this is all your homework. So I will, in the exam, I will not give you anything. I will not give you anything. So this is an example. Design, convert a BCD to XX3, and then you do it all the things. This is just like a question. Alternately, I may also ask you another question. What is that question? Convert XX3 to BCD. So now this W will now WXYZ will become the input, ABCD will become the output, and now you have different functions. Which one? Yes, don't care will change. Can you see here the don't care will change? Why the don't care will change? So for this case, the valid input, this will be the inputs, and this become the output. So now you swap it. These are the inputs and these are the output, and these are the. So this will become on the left hand side, and this will become on the right hand side, and then you derive. So now in BCD, okay. Now if you want to convert from XX3 to BCD, how many ones for A? How many ones for A? 2. How many ones for B? 1, 2, 3, 4. Yes, please.
So when you convert from XS3 to BCD, you will have 9 don't care values, right?
Why 9 don't? We will still have 6 don't care values. 0, 1, 2 is excluded. 0, 1, 2 is not there. This is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you're forgetting 10, 11, and 12. So 10 is a valid in XS3, 11 is valid in XS3. You got it? So this is 10, 11, and 12. Any question? Don't force me to cry. Okay, I'm just kidding. Okay, so now you look at here. Now we do all this magic. Okay, now we did some minimization. We did some minimization. We converted from BCD to XS3. Now we are doing some other magic. Yeah, I'm doing some. What are these steps? All these steps. Algebraic manipulation. We are doing some algebraic manipulation. This, blah, 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 blah. And then you can say these are algebraic manipulation. We get the expression for. And why we do algebraic manipulation? Logic sharing. Do the logic. And please remember, I will not ask the logic sharing in the exam. I may give you some questions for the like, how do because you know it will take a lot of time. Even if you ask me, it will also difficult for me. We do a lot of algebraic manipulation, do, but at least you should know how to minimize some function, how to do some logic sharing. So if for logic sharing, I will give you some simple question, not difficult question. But difficult question will be for the homeworks, not for the exam. Like this kind of difficult question, like how do you do logic minimization, and then you convert this in this term. Okay, this is just like the thing. So this is just for your information. Okay, and then we do the XOR mapping. Okay, we can do this later on. Okay, now I'm now finishing this thing, the lecture slide, and I will give you some now problem. Please put pen and pencil. Okay, now we did a lot of things. We did a lot of things. When we want to solve any problem, we design something. What is the first step? Specification. From that specification, then truth table. Then logic minimization. It can be the algebraic manipulation or it can be K-map. We derive the reduced expression. After the reduced expression, do what? Logic sharing. After logic sharing, implement on the mapping. It can be AND or logic, or AND logic, NAND implementation, NOR implementation, logic share, blah blah blah. This is how should we do. Now think of a scenario. Think of a scenario. We want to. So and I am you know I'm. We have a function. We say democracy is the best policy. Democracy is the best policy. And this for this democracy, we say that we have 3 inputs. And the output will be 1 when the majority say yes. Draw the truth table. And a Karnaugh map.
How many bits?
3, we have 3 people. If the people say yes, it's a yes vote. If say no, no vote. And we want to have a democratic system. The output will be 1 when majority say yes. Implement it. Now this is, what is this? Yes, please. No, what did I say? Specification. This is specification. Got it? So now please do it. I'm giving you the specification. You transform the specification into truth table, draw Karnaugh map. So now this is one example number 1. Democracy. We want to implement democracy. Okay, now we want to have a democratic system. Can we have an even function? Like 4 people? No. It should be odd. Either it can have people of 3 or people of 5 or 7. Because 4, if 2 say yes and 2 says no, no, it will not. So it has to. Please think. So now we say, if we say we want to have a democratic system, and in democracy C says, like if you say, okay, should I have a midterm or not? And I say, okay, please raise your hand. The majority says. So now help me, everyone help me. What should be the output? You can call it anything, maybe F. Then A, B, and C. A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. What should be the value of F? 0. Why 0? No. So okay, now it means 1. I may also ask maybe 1 for yes, 0 for no. If I change the description, so the truth table will change. So you say F yes, M. So if M is 1, it means majority. If it's 0, minority. Okay, 0, 1 or 0, 0, 1 or 0, 0, 1 or 1, 1. Now this says we are in the majority. Okay, now this is F1. This is F1. Now we have another function F2. Think, and you do it on your own. Okay. We want, if all of the people say yes or all of the people say no, this is F2. F2. So F2 says, it means F2 says all agree or all disagree? Yes, please. All agree or all disagree? This is also a description. So where should we have one? And the first one and the last one. What other possibility can you have? Like, think of a problem. Think. Okay, I'm stopped recording. Now we are done it here.